Okay, hello guys. So I'm sorry, I think I made a mistake and I was recording and I didn't. My screen was not. My screen was not sharing, so I don't think it's used. So I had to make this video again. Okay, so let's do it. So yeah. Sorry, it's already written because I already recorded, but then it's without screen sharing, so it's not gonna be. I'm gonna do it again. So this video is gonna be a little bit shorter because since I'm not writing, it's gonna go faster, right? But I'm gonna go over all the content. Let me put my text up. Taking like 30 minutes. Okay. So last time, let me check. This is recording and is sharing. Okay, good. So last time, we talked about that these two statements, compound statements, were equivalent. We did the tables, and we got the same tables for each of them. Well, another way to do it is show that this guy implies this guy, and this guy implies this guy. So something like if and only if. So no P or no Q, if and only if, no P and Q. Okay. So by the way, there was I like this topic because the professor that founded the first mathematical department in Colombia, where I am from, he was Italian, and he has a book about this. So how to teach this to students in high school, and he will make his own notation, and he has his own book. At that point, I mean, I was not very good at students at the beginning, but because I wanted to study engineering. But then when I decided to study mathematics, I started being very serious. And I remember this was one thing that got me respect from my friends, because since they knew I wanted to be engineer, I didn't have too much respect. But when I started, this professor invited us to go for meetings, and even he gave us breakfast sometimes. His name, yeah, he once was the creator also of an Italian school in Bogota, where I'm from, and he has this notation. And then one day I asked, I just started looking to his notes in the bus. I had to take like a bus, like it was 1 hour away from my house, and then I found a contradiction of his notation, and that was like everybody looked at me like, what? And then he said, what? And he was very old at that time, so it was me who was like nobody, who kind of destroyed his book, you know. I don't want to say his name because I don't want to mention too much of that, but it was like, man, if I want, I can be good. So it was a big discovery for me, this logic, because I never took this before, this class. So I was taking advanced classes. I never took this basic. So that's why I'm starting with this. This is so fundamental, so important for you to understand the logic behind mathematics. So you want to do this if and only if. So you need to do this guy implies this guy, and you need to make the table of the opposite. This guy implies this guy. That is this one. This guy implies this guy. So that is if and only if. So these are equivalents. It's basically a definition. You can use this one or you can use the other one. And look at, if you do no P or no Q, it's like no P or no Q implies no P and Q. So False implies false, that's true. True implies true, true. True implies true, true. And true implies true, that's true. Okay. And now if you go the other way, you go no P and Q. So this guy implies this guy. Okay. So we go this direction. False implies false, true. True implies true, true. True implies true, true. True implies true, true. Okay. So that way, this is show that it's a tautology. True, 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 true. Okay, that's what you probably want to see. Okay. So finally, after these two tables, you can conclude this. This is true. So after those two, we conclude that this is the true table. Okay, let me check here something. Okay, so so we're gonna do now is set theory, introduction to set theory. So last time I kind of give you like a very fast overview of what will be this good for, right? Where was it? On the here, right? So I showed you how the Morgan's law, it has an analogous on set theory, right? It's basically the same thing. Okay. So we're gonna work on that. So set theory. So I'm gonna use a book also. Is this book, Introduction to Analysis by Edward Gauguin. It's a very popular book. So what I like this book is that it's small. Okay, so sometimes books are too big, and then the students like, I mean, what do you really need? And this book, it will be great. We can do the whole book. I don't think we're gonna do, but that would be very ideal. Okay. And so let's start with the notion of set. What is a set? So we shall think of a set as a collection of objects. Okay. So it's more an intuitional idea. Okay. So think on the universe. Okay. So we have example. These are more mathematical, right? Examples, but you can just think the set of people that go to your university, that's a set. Okay, all the people in the state of Texas, for example, that go to UTRGV, that's a set. Okay. Also, as I said, it's good. We need to determine the universal set. So the natural numbers, for example, this is a set. All right. The alphabet, or the roots of polynomial s cubed plus 1 equals 0. That's a set. Okay. Definition: if A and B are sets, then two sets are equal if and only if every object belonging to A it also belongs to B, and if every object belonging to B also belongs to A. Okay. So that's what it makes sense, right? Like, no, there's no, but this writing these kind of definitions is very important to set up, okay, what is what and how can we use it. Definition: if A is a set and X is an object that belongs to A, we say X is an element of A. Okay, that's also very logic, even trivial. And we write X belongs to A. So that's that notation I need. If X does not belong to A, we write X does not belong to A. Okay, that's That's notation. So we want this notation. Okay. So definition: if A is a subset of B and B is a subset of A, and A is not equals to B, then A is a proper subset of B. Okay, hold on. What? Definition. Okay, okay. Oh yeah, this definition is okay. If A is oh no, I put it wrong. Sorry. This is if A is a subset of B and B is a subset of A. Oh, okay, okay, okay. Yeah, yeah. Sorry, I didn't write it correctly. So this means A is a subset of B, and it means every element of A is in B. If every element of B is in A, every element of B is in A, then we use this notation. And this is every element of A is in B. And if they are different, but and if A is subset of B and they are not equal, then A is a proper subset of B. Okay. Sorry, since I recorded this, since my previous recorded failed, so I was simplifying here. I didn't write the whole thing, so that's what it looks messy. But okay, I'm glad. This is the meaning. Okay, so that's just notation, right? A subset of B, B subset of A. So next, I want to give you an idea of the power of this. Okay, what do we care about set theory? Well, this is so powerful because there is a famous construction of the natural numbers. How do you construct natural numbers? From nothing. Okay, from nothing. So there is a code that I like. That I say the mathematics is made by the human being, but the universe, no, we didn't make the universe. We are just here, like we're passing through. We don't understand how the particles move. We see a table, and we see a table, but we don't see the particles. We don't see the electron. We don't see how the tiny everything is, right? And if we go big, is the universe finite or infinite? Do the universe has an end? And if it has an end, what is happening after that? You know, and so it's growing or not growing. So we have so many ideas and no questions. But on mathematics, we had made this universe. We made this universe. So that's why I said here, we're a mathematical God. Humans are the mathematical God with a small g, right? How to construct the real numbers? So how do you construct the real numbers from nothing? You have nothing. Well, let make that thing to count something. So you call the nothing the empty set. Okay. And now let's put that empty set on something. So there is an assumption there in this construction that is saying that nothing can be put on something. So you can construct something out of nothing. So this is, you put it here, you pack it somewhere, and that's what I'm gonna call one, because it has one element. Okay. Now, how do you make two? You put the empty set and the one in one set. So how many elements has? One and two. So you are making the universe. So how do you make number three? So you get the empty set, the one and the two on the same set. Okay. So that you call it three. and so on. So that's a construction of the natural numbers. But you know, it has to be more rigorous. This is very sketchy. But you know, I want to give it to you because I mean, you guys, if this you have to take a whole logic class, and this class is kind of trying to show you many things of mathematics that make you interested to keep pursuing your master degree. So useful sets. You have the natural numbers 1, 2, 3, 4, 5, 6, 7. You have the integers 1, 2, 3, 4, 0, minus 1, minus 2, minus 3, right? Then you have the rational numbers. That is a countable set, right? 0, 1/2, 1/3, 1/4, and so on. Then you have the real numbers that you have all these guys, the natural, the integers, and the rational numbers, and more. You have the square root of 2, pi, and e. And these weird numbers are called transcendental numbers. Also, something that I was mentioning here is that the natural numbers, of course, is an infinite set. This is called the cardinality of the set. So the cardinality of the set is infinite. And also the cardinality of the rational numbers is infinite, of course. And the cardinality of the real numbers is also infinite. But how infinite it is, okay? Which infinite is bigger, okay? So this is like logic, advanced logic. So the cardinality of the natural numbers is kind of, let's call it like that, like a left zero. This is a funny number, but it's the cardinality of the natural numbers. Turns out that the infinite of the natural numbers and the infinite of the rational numbers is the same. So amazingly, the rational numbers are countable. Send me an email if you are interested to see the proof, or you can look on the proof on Ted and Sostrom. Okay, in the book of Ted and Sostrom. But turns out the real numbers, the infinite of the real numbers, is more huge than that. So it's like 2 to the power epsilon. Okay, so the infinite of the real numbers is much bigger than the infinite of the natural numbers are the rational number. That's, you are interested? Well, learn some logic. Okay? There's some people that study those things. Okay, now what is with the real numbers? These numbers are square root 2, pi, and the exponential. Those turns out that are the limit of the sequence of rational numbers. Okay, I think you remember you proved once. I think you proved. Yeah, so well, let's leave it for later. But you can make a sequence of numbers. You know sequences because you learn calculus, right? But we're gonna see next week. We're gonna see it rigorously. So you have a sequence of natural number or numbers, no natural numbers, rational numbers, converging to something, and that's a square root of 2, for example. You can make a sequence of rational numbers converging to the square root of 2. You can make a sequence of rational numbers converging to pi, and this one you did always you do this one in calculus. Okay, do you remember what is the sequence? What is the sequence? Limit of n goes to infinity of something that gives you e to the 1. Remember that? Remember what is that? So what is it? You guys remember? Well, go and look to your calculus 1 class. I'll tell you next time. So what is here? So what is the sequence that converges to the exponential? And this is incredible because Pythagoreans spend their lives studying these transcendental numbers. And today we just, in calculus 1, we just get this 2,000, 3,000 knowledge of mathematics so fast. Okay, we don't appreciate it that much. Okay, so for you choose two numbers on the real numbers, you can make an interval A and B, and then you go let the x in the real numbers. So these A, B are real numbers. The interval are all the x between A and B, right? A is less or equal than x, and x is less or equal than B. So the interval is A and B. So you're considering this, okay? This one are, this is closed, this is open, and this is all these numbers. So those are the intervals, right? So same definition for A and B, right? So for A and B, so it will be something like open and close. And here open and open. Okay? So operation between sets. So this is gonna be important, very important. That's what I'm saying again. If you see the preliminaries from your book of analysis and your book from Astral Algebra, both talk about sets, because with sets that's how you define functions. And without functions, you don't have calculus. Without functions, you don't have algebra. So functions is fundamental. Relations and functions. Okay. Okay. So let A, B be sets. The union of A and B, written A union B, is defined to be the set of all objects that belong either to A or B, or possibly both. So this is your universal set. You need to take the X from a universal set. And so you're going to take the point that belongs to A, union the point that belongs to B. Okay. Definition of intersection. So you're going to take the point that belongs to A and also the point that belongs to B. Okay, this is this one. Okay, we already saw that before. So, and now I wanted to do an example. So, oh no, so let's say A equals C, D, E, and let's say B equals 1, 5, 6, D, and then let's make, oh, not D, oh, this is going to be confusing. Okay, so let's make it smaller. So it has to be the same notation, right? C, D, E. So I don't make some confusions. D. And C, let's call it 1, 2, 3, 4, 5, 6. So we do A intersection B. What is this? So you need to see who is common. So that will be D. If you look A intersection C, what do you get? You get nothing. So you get the empty set. So that's don't yeah, just write it like that. Don't write it like this. Okay, just empty set, just like this. And then if you do B union C, you just put together 1, 2, 3, 4, 5, 6, and union D. So 1, 2, 3, 4, 5, 6, union D. Okay, so that's kind of how do you operate those. So you're gonna have some some statements to prove in your we're gonna do Morgan's law. Okay, but let's do one first. So we're gonna do our first proof. Okay, so theorem. They A, B, C, B sets. Then A intersection B equals B intersection A. Okay, and we have so many. I'm gonna write all these. A union. We're not gonna do all this. We're just gonna do a few. B union A. A intersection B intersection C equals A intersection B intersection C. So this is basically commutative. So these are commutative, because yeah, you have this A union B is the same as B union A, because it doesn't matter for a set. For example, A intersection B or B union C. So B union C is the same that 2, 3, D, 4, 5, 1. The order doesn't matter. Okay, there is no order here in this inside the set. So that's why these are commutative. Okay. So for the is associative of the union. Okay, all these are, they look kind of silly, but it's important. There are things that structure in mathematics that doesn't satisfy. Intersection B union C, that's more interesting. That's A intersection B union A intersection C. And then 6, A union B intersection C, A union B intersection A union C. So there is a way, you know, there is a way, and some advantage of the book of Ted Sundstrom. The book by this guy, mathematical reasoning. So is that he shows you that there is a process. There is a process to make a proof. Your book of analysis and algebra are not going to show you that there is a process. Okay, they're not going to show you their process to find the proof. They're just going to tell you this is the proof. They're not going to tell you how do I get there. They just said, okay, this is the proof. This is how I write it. Okay, that's it. So I'm going to show you my process. Okay, I'm going to show you the process of how to make proofs, my personal way to make proofs, but it makes sense how Ted Sundstrom explain it. Okay, usually, you know, you always make a bubble. Like you just start wondering, okay, this is what I have. These are the definitions I have. Then you jump, this is what I need to prove. Okay, so how do I connect what I need to prove versus what I need? Okay, so let's prove the first one. Proof. So the first one says A intersection B equals B intersection A. So that means I need to prove that A intersection B is a subset of B intersection A, and I need to prove B intersection A is a subset of A intersection B. Okay, but that could be one way to do it. Okay, but really there is another way to do this, and it's directly by definition. Okay, so first there is this method and I'm gonna go over this using the book because the is so much writing. So maybe if you want to read it, you can read it, but I'm gonna try to explain it in a different way, kind of connecting with testosterone. So first, so I will call it bubble. Then there is this method that testosterone called known show table. Okay, and then you write it down. Write your proof. So what is my bubble? So my bubble is, okay, this is A intersection B. So let's say A, B is an universal set. A intersection B is this one. A intersection B. If I do B intersection A, so I have B. So first goes B, right? So, okay, so let's do it like this. A intersection B, so I have A, and then I have B, so I have B, so the overlap is this one. If I do B intersection A, so first I do B, and then I do A. So that way, you see these two things are the same. So indeed, that has to be true. So first, first you have to make a bubble, because sometimes things are not true. So you need to play around it. If it's about numbers, you use the bubble should be about numbers. Oh, this is true, this is not. Can I find a counterexample? Okay. So the bubble is good. So for the no-show table, so if you say, so for the no-show table, it's you start with basically definitions. So what do I know? What do I know? So if X belongs to A intersection B, what do I know? By definition, this is if and only if X belongs to A and X belongs to B. Why? Definition. This is by definition. Okay. Now, what does it mean? So I calculate, and on the other side, what does it mean X belongs to B intersection A? So what does it mean to this thing to be equal? Remember, that was the first definition we said. So two sets are equal if every element of X in this set is in this set, and if every element of this set is in this set. Okay. So that's this. Every element of this set is in this set, and every element of this set is in this set. Okay, that's one way to do it. Or I can do it directly. So what does it belong? X belongs to B intersection A. It means if and only if X belongs to B and X belongs to A. But look at, are they the same? X belongs to A and X belongs to B, X belongs to B and X belongs to A is the same. They're equivalent. It's just the order. Does the order matter? No. So there is an equivalence right here. Okay. So how do you write your proof? So they like to use here a table. I'm gonna put it like this, like how Dr. Ted Sundstrom put it. So I mean, he makes the effort to organize it somehow. So I give him the credit. I think might be useful for some of you. What is the step? So the step is first, a statement, what we know. So we know that X belongs to A, X belongs to A intersection B. Okay. But by definition, so I'm going to put here, this is hypothesis. Hypothesis. So this is the reason. X belongs to B, A, that's a hypothesis. Okay. So, but then by definition, X belongs to A and X belongs to B. Okay. And now that I had my sketch, because I have my sketch right here, you see? So I can say, probably we need to find an argument here. So, but this is the same that X belongs to B and X belongs to A. This is only, well, we'll see. Also, this can be written equivalently as this, right? Then by definition, X belongs to B and X belongs to, oh, sorry, that means, sorry, by definition, this means X belongs to B intersection A. Okay, so this is so easy that it's kind of, you know, it's like too tedious to organize, but you know, we're doing our first proof ever, so we're in the class, right? So this is how I put it. So that's how you write it. Let's write it. So write out your proof. So let X in A intersection B. Okay. Okay, let's start better. By hypothesis, so then let's consider X belongs to A intersection B. You can put it by hypothesis. Okay. Then by definition, a definition of intersection, this means X belongs to A and X belongs to B. Equivalently, sorry, I can't even pronounce it. This can be written as X belongs to B and X belongs to A. Okay. By definition, this means X belongs to B in intersection A. So I think what we have done here is proof. Therefore, we have proven A intersection B is a subset of B intersection A. Okay, so that's, I remember when we said that it's a subset. So similarly, Similarly, we prove B intersection A is a subset of A intersection B. Okay, so this is, you saw this one. So all of them are very similar. Okay, so this is about sets. So let's do one proof now that we are into this business. Oh, let me give one more definition, and then I'm gonna give you a homework. Okay, so we can do some. We move on to other kind of proofs. Okay, so let me define. So you can do your homework. So definition. Let A and B sets. Then the complement of A relative to B is written B minus A. Okay. In other words, this is B minus A is, there are all the X. So in the book, they don't use universal set. I think they already assume X such that X belongs to B and X does not belong to A. Okay, let me give you 30 seconds to graph me that. What is this set? So how do we graph that? So you have your universal set, you have A, you have B. So it's all the X that belongs to B and X does not belong to A. X belongs to B. You see, all these are the X that belongs to B. But X doesn't belong to A. So we need to raise the intersection. Oh, sorry. Let's see. B, A. So it's these guys. So that's the only. It's B without A. So is this true? What could be a theorem, a proposition we could make ourselves? We could say that is B minus A is equals to B minus A intersection B. Right? And yeah, that's true, right? Probably unnecessary because we already took in the elements on A. Yeah. Okay, that's good. But there are other ways to write this. So how do you make a proposition? How do you make a theorem? So let's say have it like that. How could we make a theorem out of this? B minus A. Here I'm improvising, okay? So like I show you like how a mathematician works. So I would like to make it an intersection of two things. How can I make B minus A an intersection of two things? So yeah, so I think I could do like this. Of course, I have done it before, I imagine. So A, so I don't want anything on A. So I could take A, the whole A out of A, right? So I'll take A complement. That's also, okay, the notation for that is A complement is the universal set minus A. Okay. Intersection B. And what is B? B is all this. But you see, only the part that I want is this. That's exactly intersection B. So this is a proposition. B minus A equals A complement intersection B. So you see, that's how you can make your proposition, your statements, your theorems. If you have a bubble, you can make your statement. So try to prove this. So this exercise. And you kind of see it right here, right? Because X doesn't belong to A means it's in A complement. X belongs to B is right here. So that will be basically the same definition. Okay, so let me see. Let's make one last proof, so I can assign you a couple of proofs. And they have. Let's do this one that the book spent a lot of time doing it. I'm gonna do it super fast because because I'm live, right? So because this is a book, you have to read the whole thing to understand the analysis. So I'm gonna make it short. I mean, since I'm talking, while I'm talking, I'm doing a lot of what the book is explaining. So, and again, I'm gonna do my own reasoning. So I think that's the fun of it. I don't wanna exactly copy paste the book or the books. I do my own stuff. But I think I like this from this book. I like this organizing. So let's do this proposition. Proposition. If X and Y are odd integers, then X times Y is an odd integer. Okay. So what is an odd integer? So we need the definition. Without definition, you cannot even start. So an integer A is an even integer provided that there exists, and then I'm gonna use this in a second, that there exists an integer n such that A equals 2n. And then an integer A let's call it to avoid confusion. An integer B is an odd integer provided there exists an integer n such that A equals 2n plus 1. Okay. B, right? So I'm using A for the events integers, and I'm using B for the integers numbers because a joke. Okay. So there was a class, so it was Monday, right? So it's a cartoon actually. So there is class, and they said Monday says the conclusion of the class, okay, they're solving an equation. The teacher said that, so X equals 2. And then on Tuesday, they start doing another problem in mathematics. And then the teacher said, so X equals 3. So Juan raised his hand and said, hold on a damn minute. You just said yesterday that X was 2. So that's the joke. So that's what but for that joke, I prefer to use A and then B. So you guys don't, because if I write A even and B odd, it's probably clearer that if I write A even and A odd the same, but just, of course, there is no, because it's mathematics, you can use the same letter, okay, in the same definition. There is no mistake here. But you know, there might be some Juan that cannot raise, Juanito, they cannot raise their hand and say it, right? We just use, for the jokes in Colombia, we also, for some reason in Colombia, the student that asks all the questions, they call it Juanito, Juanito Preguntón. Juan, the question, the one that question everything. Okay, so let's do it. So how I'll do this? Okay, the proposition is, if x and y are odd integers, then x times y is an odd integer. So first I'm gonna make a bubble. So I could just start my definition, let this and this and this, and then you don't see my thinking. But since this class is about teaching you to think, so x is an integer. So since x integer means, what does it mean? It means there exists, sorry, an integer, x and y, odd integer, right? Not just an integer. X is an odd integer. X is a odd integer. So what does it mean? It means, and look at this notation, exist and such that x equals 2 times n plus 1 by definition, right? This is by definition. By definition. So let's make some kind of mixture between tables and arguments, etc. So y is also an odd integer. Then there exists, let's call it m. This time you cannot use the same letter n, because then it will be the same number. Okay, that's important difference. This is m such that y equals 2m plus 1. Okay, this is by definition. So next, it says the proposition x times y is an odd integer. Okay, so what I need to show, so this is part of traditional technique. X times y is an odd integer. That's what I want to prove. This is what I want to prove. So you need to know what you want to prove. That's a big mistake for a lot of us starting to prove. Always at the end, write what you want. If you don't know what you want, you cannot get there. You need to know what you want. In life, what you want. You want to have a family, you want to be a big professional, you want to live in the biggest city possible, you want to be happy, or you want to be rich, or you want to be close to your family, whatever. You know, I don't know what you want. But here, all that we know is that we want to show that x and y is an odd integer. What does it mean? It means, and we are going backwards now, by definition, that there exists m, n, another popular letter could be s. There exists s, and s has to be what? So there must be an integer. So let's say there is this x that is an integer. So I have to say here m is an integer. And I have to say here n is an integer. Okay. Because that's going to be very important. Otherwise, my proof is going to be wrong. I need to say where those, it is s that is an integer such that s, oh, sorry, x times y equals 2 times s plus 1. Okay. That's to me, that means to show that this guy is an integer. Okay, so I need to come up with s. What could be s? So this is the all this is the reasoning, intuition, math skills, call it whatever. So, but it's there. So what do I have? I have one integer called n. I have another integer called m, right? So, but what I need x times y. So I'm gonna do x times y. So I need x times y. So I do x times y. But look at by definition of x and y, I can replace this by 2m plus 1 times 2m plus 1, right? So this is this step makes sense because I am by the values of x and y. Okay. So, but now by product of integers, by product of integers, I can do those. 2 times n times 2m, I get 4nm plus 2n plus 2n plus 1. That's the product of integers. Okay. Product of integers and distribution and distributive property. Okay. So now it turns out that x and y equals to this. So I need to come up with an s. That's my whole point. I need an s that is an integer. And I need that 2 times s is that. So any idea what could be your s? So this is when you make your, this is what you do, your, if you want your trick or your intuition. Oh no. This is what you need your math skill. So you said, okay, so this guy has, you just, some people just call it, just look at it. If you just look at it, your brain is gonna process and say, let's factor 2. If you factor 2, you get 2nn plus n plus m plus 1. Okay. Sometimes you said, okay, I just gonna factor because I can, or I need to factor 2 because it needs to look like that. And look at, now you look at it and you say, oh, look at this guy here. Is that my S? That could be your S. So this could be your S, but what happens with S? S must be an integer. Is this an integer? Is this an integer? Why is this an integer? Because I said n is an integer and I said m is an integer. If you don't put that on, if I don't put that on, I will be missing points because that needs to be an integer. So this guy is an integer So multiplication of integers is an integer. So n times m is an integer because they're integers. Plus an integer, that's also an integer. So we can, instead of saying trick and definition of that, so now you said, because multiplication of integers and addition of integers is an integer. S is an integer. Definition. Okay, so that guy is an integer. So since S is an integer, we have that exists as integer such that 2xy equals 2s plus 1. Therefore, xy is an odd integer. Okay, so that's the proof. Okay, how an arrogant book would write the proof. Okay, so this is how you think. That's the bubble that you have to put together. How do you write? How a book write it? How a book or a paper write it down? So because it's different, right? Or a paper will write it. Let's see. I will probably write it like this. Proof. Okay, proof. Proof of what? If x and y are integers, then x and y is an integer. That's what I'm going to prove. Proof. Let x and y are integers. Right? Let x and y be odd integers. Therefore, there exists m that belongs to integers. Oh no, n, right? N and n belongs to the integers such that x equals 2n plus 1 and y equals 2n plus 1. Okay. Therefore, if we consider S equals 2nn plus n, we obtain x times y equals 2 times s plus 1. S belongs to integers as we want it. Okay, that's probably like a short proof. So some part of the job is okay. So why is, so as a student you read this, you said okay, what? So you are skipping why s is an integer. So you have to think, oh, why is that s in integer? And you said, oh yeah, because this and this and this. So that's the difference of how a book write the proof and how is the real process. Okay. Okay. So I think for today we can stop here. I'm gonna give you a lot of easy homework about sets, about little proofs, about connectors, and about this. So remember, I didn't say it too specifically, but this means exist, and this means for all x belongs to A. For example, for all x belongs to A, this is exists. These are quantifiers. Let's see. This is on section 2 point. Let's see. So quantifiers and negations. Quantifiers and negations. So this is on page 63. Okay. So it says for every an existing quantifier. So we will do, we're gonna start using those a lot. Okay. So I think, yeah, those are enough. And then the section of set theory was page 215 from the book of TED and Substron. So I give you that reference so you guys can go on and do more stuff, read more if you want, but I think pretty much we did. Also, he talks about cardinality, more examples, and then there are more exercise of proving stuff. Okay, so we'll do that. So, but I'm not too much in a hurry because we will do a lot of those problems in the homework. Okay, so now next class I'm gonna define functions, and then we can start doing more exercises. But now I think now we are in the right track. Okay, we're doing more mathematics now. Okay, good. So I'm gonna leave it here. I'm gonna make it shorter because I don't want to put more stuff. Probably at this point I want you to explore all the problems I'm gonna give you in web work so you can move forward. Thank you.